And yes, all the material that you find here, you can reuse it. And yes, it has been simplified. So you have applied previous selections, so you can handle all the data samples more easily. Okay. Well, as you have seen through the lessons this week, so nowadays there are a lot of different packages that you can use for machine learning. At LHCb, I actually started using root and the package TMDA from root in order to do applied machine learning. However, nowadays I think that there are many other options with a nicer interface with Python, like scikit-learn. Here we will use scikit-learn together with pandas and NumPy, and I think most of the problems, you can solve them at LHCb using just these three things. What I have used so far, so in general, you can use almost all the different machine learning possibilities on an experiment. However, in general, what I have used the most is the supervised learning, so both classification and regression. And here the problems will be based on a classification. So in general classification, I have used it in order to remove signal background and preserve the signal, a certain signal. And then regression is, I have used it in order to improve the simulation. So you take data, you take simulation, and you make your simulation to look more close to your data than it was before. And yeah, so the task in general is, okay, you have a background component. This is of course super simplified. Background component that is an exponential, a signal peak here, and what you want to do is to remove all this background. So based on the topology of the decay and of a certain decay, so this is a particle, this is a k-short actually, and for example, a k-short of pi, and you want to get a pure sample or a more pure sample of k-shorted by pi than you had before. And in order to do this, you can apply machine learning in order to remove the background and end up with a distribution that looks like the plot on the right. So you have a very small background component, and you maybe have lost 10% of signal efficiency, but you have removed a 90% of background. And in general, applying machine learning algorithms is more efficient than rectangular cuts. This was used before. So, for example, applying cuts on quantities like the transverse momentum of the particles. So the lessons and the sample they come from proton-proton collisions, both simulated samples and real data samples collected by the LHCb experiment. So we are on a collider experiment. So we have protons coming from the left, protons coming from the right, and they collide in this point here. They produce particles, the particles decay, and then you reconstruct these tracks that you can see here in colored lines. And so the idea here is to identify a neutral particle going to two charged tracks, so a positive track and a negative track, so bending on opposite directions. So you start combining the different lines that you can see here, and you get candidates, and then you have to filter these candidates and distinguish your signal from all of these candidates. So imagine that we want to identify this candidate that has been created from this green track here and this green track here from all the rest of the event. Okay, so this is a hard task that we can solve using machine learning. And yes, in the challenges that I'm presenting, so the first and most simple challenge is to identify the k-short by pi decay in simulated data inside all this in this environment, using only topological and kinematic information. So the information about the decay itself and kinematics. So what I was thinking to do is to start downloading the package. It's a standard Python package, so you can download it and then install it using pip or conda or whatever you want. And then there are notebooks inside. So my idea is that we start downloading, so everyone downloads the package, starts installing it. because it takes like 5 minutes probably to download all the samples. And in the meantime, I started explaining the first challenge or the first notebook. So I don't know if that's okay with you. So yes, you can either, I don't know if Xavi provided the link to my GitLab. Did you, Xavi?
I don't remember, to be honest. Maybe it's better to post it in the chat window.
It's in the,
if not, people just can click in the slide. Also, that should also work.
Yeah. So if you click in the slide, it goes to my GitLab, and now I have to share the other. Okay. Okay, so this is my GitLab. Once you click in the link on the presentation, so it goes to my GitLab account, and here you can download the package. This button here, download, and you download from the source code in zip format or whatever format you want. And once you do this, you just need to unzip the package, and then you can install it using pip, or if you have Conda, you can use it pip from Conda, or if you're using a virtual environment, again, you use pip in order to install it. I don't know if everyone uses to use these kind of things. So just to demonstrate, maybe I can demonstrate how to do it. So yes, inside the virtual environment is just doing the pip install. So this is the package, you can see, and here you just need to do pip install -a. And of course, I have already installed the package, so it has nothing to do. But for you, it will take maybe 5 minutes.
The link is now in the chat. Sorry to interrupt.
No, good. So I will wait maybe 5 minutes so everybody downloads this and starts installing the package.
Sorry, Xavi. It says that the chat is only available for the members of the team.
Okay. If not,
let me put it. Wait.
Yeah, I will put it in Indico. Okay. In Miguel's Miguel's entry in Indico today.
Okay, if not, you can see, I think I'm sharing now my browser. So if not, you can copy the link on the very top.
Now it's in the Indico's timetable as well.
So, how are you doing now? Did anyone manage to start installing it?
Yes.
Okay. So, if everyone has done it, and maybe you can start jumping into the first notebook. So now you should have one script available called have lessons ML. Let me now. Yeah, you should have this script visible in your system. If not, I mean, the first notebook is inside have lessons ML. You have notebooks, and here you start opening with Jupyter the introduction notebook, and that's it. Is essentially the same. It will do the same thing. So let me open it, and let's share now. This guy here. Okay. Good. So I will go to the first. So these are two different challenges. These two. We will start with the first one, which is more easy. And this is using, again, to remind you, proton collisions. This is all simulation. So what I did has been to take proton collisions in IGFAE 8 at an energy of 450 GeV, which is close to the SPS energy at CERN, and then process this sample in order to do the combinations, do a preselection, and also emulate the effects, so the resolution effects of an experiment at the SPS. Okay. So the challenge is to identify the short-wave pi candidates from the whole sample. Of course, since this is a simulation, you can play around and separate directly the short-wave pi from other components, whatever, lambda to proton pion, phi to mu, or you can just start exploring the data samples to find other decays of interest. So on the, first I start with some imports. Scikit-learn, matplotlib. And first thing we have to do is, of course, load the sample and then define the signal. We consider signal and what we consider a background. So to separate signal from background, I have some variables in this sample, which are called PID, so particle identification, and it's a number that is set by convention. So every particle has its own number, and for example, pi plus is 211, and pi minus is minus 211. This is a PDG convention. It's a convention set by the particle data group, and you can consult it in the web. And then what I do is to guess the mother. I ask the head particle to be a k-short with the number 310. And then this RID is simply a number that identifies the particle within the same event. So I'm asking the two decay products to come from the same head to define the signal. Okay, since the branching fraction of k shorted by pi is very, very high, I don't really need to apply any other requirement to get the signal. So as you can see, the signal is defined like this. Then I'm defining a set of variables, and these are the variables you can play with, because the others might be related to the simulation, information of the simulation, and not of the decay itself. But yes, here you have first of all kinematical variables like the momentum of the head particles, so of your K-short candidate, the transverse momentum, the lifetime multiplied by the speed of light, flight distance, also the momentum, transverse momentum of the decay products. Then the impact parameters, which are the distance of the extrapolation of the tracks to the extrapolation of the tracks, the distance between this extrapolation and the proton-proton collision point. And then some vertex-related quantities like the position of the primary vertex and of the decay vertex of the K-short, and also the distance of closest approach between the two tracks, the two parent tracks. So then, yes, I'm displaying them. And yes, you have to define the train candidates. So this is a function that I created in order to split the sample in train and test and define what is train and what is test. And here I'm using 2/3 of the sample for training and 1/3 for testing. And this is important because then you want to do a study over training on your algorithm, and you need a completely unbiased sample. So a sample your classifier didn't train in order to do this kind of checks of for overtraining. Okay, so this is defining in sample a new column called train that defines the training sample. And yes, then the next thing I'm doing is, okay, I'm defining the classifier because this is one of the first things you need to do, to choose the classifier. And here you can play with it. I'm using an adaptive Boost decision tree classifier. And this is because in my experience in these kind of problems, of classification problems at the LHCb, it performs very well. But of course, you can try to use neural networks or any other classifier that you like. You can play with the different parameters and also with the different variables. So here I have chosen these variables because I know that they will perform well because of my knowledge of strange decays at LHCb. But you can also start including here secondary vertex position or any other quantities, or use the amount of quantities. You can also combine them. So instead of adding the impact parameters, for example, you can previously calculate the minimum impact parameter and include it as a variable instead of these two. Okay, so you can play with them. So in order to determine the variables to use, so I have created another notebook, and you can find the link here, this notebook, because it's worth before training the algorithm to check the samples in order to determine what variables to use. So there are many different ways of choosing. I mean, there is no deterministic way to choose the variables. So it's a matter of trying, but you can get some hints doing some studies on your sample. So the first thing you can do is, okay, again, import, load the sample, define what the signal. And here, the first thing that I'm doing is to simply plot the distribution of the variables. Okay, and you can see that the distance of closest approach is different between signal and background. You can see that the impact parameters is also of the daughters is very, very different with respect to the background. And this is because the K-short is a particle that lives a lot for these energies. And so this means that the impact parameter of the daughters will tend to be high, very high. Okay, so it's a very good variable to use to discriminate signal. And yes, in general, then I also included the transverse momentum. You can see that the agreement is better with respect to background. However, in general, in these experiments, the transverse momentum is correct. All the variables are correlated with the transverse momentum, so it's a good idea to include them in the classifier. So this is where I get them.
Sorry, Miguel, just for my curiosity. So you have something which is called head and P1, P2. What are they? I guess what it is, but maybe you can.
So yeah, maybe I didn't explain it correctly before. So the head, so you combine the particles. So you take one positively charged particle or track, and this is called P1 in the sample, and the negative one is called P2. So these would correspond to your pion candidates. And then the head is, of course, the gate-short candidate, so the combination of the two. So you combine the two, and from this combination, you can start calculating the momentum, impact parameter, etc. So this is what is called head here.
Okay, thank you.
Okay, next thing. Yes, so even if the distributions look, they are similar for background and signal, the machine learning algorithm will the machine learning algorithm will actually work in such a way that it can also profit from the correlation between them. So it's also good to check the correlation, and this is done in the next cell. And yeah, in general, people used to construct these two matrices, so for signal on the left and for background on the right, and you can see that they are different. So for example, the biggest difference is found on the, I think it's the transverse momentum of the daughters with respect to the impact parameter. So yes, if you look at this number, so P1 PT versus P1 IP, so this is 0.36, and here is minus 0.0327. So it's different. And the machine learning algorithm will exploit this information in order to discriminate your signal. So yes, in general, if you start seeing a very high correlation between two variables, sometimes it's better to remove one of them because it doesn't really add anything to your algorithm, and you might end up with a curse of dimensionality, and your algorithm will perform worse. Then another thing that you can do is also to rank the variables. So again, there is no way to determine what variables to use, but you can kind of, and you cannot really know the performance of your variables till you really train the algorithm. But what you can do is, yes, again, you can kind of get a hint of what variables to use by running a simple classifier before your main classifier, let's say, and get the feature importances from this classifier. So here I just trained a decision tree classifier in my sample, and I obtained the feature importances from it. And yes, you can see them here. So you have the impact parameters that are the most important of the particles, followed by the transverse momentum, and finally the distance of closest approach. Again, you can also try to change this classifier and see what happens with this ranking, because it might change, but still, in general, you will find that the impact parameters will be always on the top of this list. And yes, then there is another thing that you can in general do also to improve your classifier, and it has to do with the fact that you use simulation to study real data. And in general, simulation, the first rule of Monte Carlo is never trust your Monte Carlo. So you will always find discrepancies between simulated data and real data. And people in general, and I have also done it, what we do is to weight our simulation using a regression. So you can use, for example, Rydlin-Booston in order to do a regression and make your simulation be closer to your real data. This is something that I just wrote here, but we are not going to use it. But in real life, you might want to make use of this package that is HepML, that was done by Andre, I think, and a handful in order to handle this problem of these regressions problems in particle physics. Okay, so once we have studied the variables and we more or less have a set of them that they are good candidates for our classifier, so we go back and we fit our classifier to the data sample. So providing the variables and then the signal mask. And then once it's fitted, I can start predicting the probabilities of the sample. Here I'm applying it to both the training. So this is the whole sample. So I'm applying it to both the training and test samples. And you can see that it's returning a background probability and also the signal probability. Okay. And now we have to check that the algorithm is actually doing what we want to do. So what I have done is to simply plot the invariant mass of the K-short and see how the background evolves with the mass, okay? And I get this thing here. So yes, you can see that without requirement, on the lower part, you have your background and it's being reduced by the classifier after applying this requirement on the signal probability. And yes, on the right, you can see an animation of what happens when you require the signal probability greater than a certain number. And you can see that more or less it will reach 0.5, then I will go down again. This has of course been scaled. So around 0.5, you maintain more or less the same signal efficiency. So you don't almost lose signal. Now we really want to evaluate this performance. So to design a figure of merit, or also to determine if this algorithm is better than the other or not. But yeah, first I think that I have done the overtraining check. So the overtraining check is important in order to check whether your algorithm has not been overtrained, so it will perform in the same way on a different signal sample. So this is done simply by plotting training, so the training and test samples for both background and signal, and they must agree. And you can see that the agreement is quite good between all of them. And you can also see that here this can be used also as a figure of, well, not figure of merit, but you can use it also to determine whether the algorithm is performing better, an algorithm is doing it better than other or not. But in general, what is used as a figure of merit is the RAC curve. So this you have already seen this week. And people in general, well, fine. I used to plot it in signal efficiency versus background projection. You can find it also on the other way around, so background projection versus signal efficiency, but more or less at the end is the same thing. So what you want is this curve to be, the area of this curve to be as close as one as possible. Okay, so this you can use in order to check when you play with the algorithms and the variables and so on. You can play with it so you get a better area under the curve. Again, I don't know if it was explained before, but I will maybe repeat it here. So in general, this RAC curve, it completely depends the performance also on what you want to do. So sometimes for searches and verse searches, you want a very high background rejection, so you really move to this part here of the RAC curve. You don't really care about the rest. But sometimes what you want is larger data samples, so you want to maintain a very high signal efficiency. So you are more interested in this region here. So the performance of the algorithm also depends on the search and on the kind of analysis you're doing. So yes, sometimes this area under the curve is cannot really used only as a figure of merit because of that. Because you might find an algorithm with a better area under the curve, but that performs really bad in this region here, and another algorithm that does it very good in this part here, but then this region it doesn't perform well, and you would prefer the first one versus the second, for example, on a search for a rare decay. But yes, next thing, so also very important is to study the correlation with variables of interest. So this is K-shorted by pi. So imagine that we want to fit the K-shorted by pi distribution. So we want to fit the dipion invariant mass. So we don't want our classifiers or requirement on the classifier to bias the mass a lot, because we might end up with distributions. So we might modify the background distribution so we cannot distinguish it from the signal. So here, what I have done is simply to plot the signal probability versus the invariant mass. You can see that more or less we get a flat distribution, so the correlation is very small. you will always find some correlation. It's normal because the certain variables, and for example, if you start including track quality variables in your classifier, the resolution, so for a higher signal probability, the resolution will be better. So it means that, for example, for signal, you will get a more narrow peak when you ask your sample to have a signal probability greater than 0.5, let's say. Okay, so it will bias the mass, but yes, you don't want really weird things in this plot, and you want the correlation to be as smooth, to evolve as smooth as possible. So in order to see the effect of including the mass or on the classifier, so I have included it here. I have retrained the algorithm, and you can see what happens. Okay, you can see that we have, in principle, we have trained the algorithm using the mass, and you see, in principle, we have a very good background rejection. But however, when you look at the Bayesian invariant mass distribution, you find this. Okay, so you find that before the background after requirement on the classifier was like this, so this green curve here. But then when in the new classifier, when you apply this requirement, your background has been modified, and now it looks really like the signal. So if you want really to plot if you want to fit this distribution, you might end up in a situation where you cannot really distinguish signal from background, and this can turn very, very dangerous in your analysis, and you might end up also having, for example, increased uncertainties due to this. And yes, you can see that on the plot on the right. So this is the signal probability as a function of the invariant mass again, and you can see that our classifier really increases the signal probability for background candidates around the nominal mass of the K-short. And this is something that you, in general, you want to avoid. This doesn't only happen when you include the mass directly in your classifier, but if you're, for example, in adaptive boosted decision trees, if your classifier is deep enough, then if you provide quantities that can be used to compute the mass, so for example, you can use the lifetime, the momentum, and the flight distance of the particle in order to calculate the mass. And if your classifier knows about this, you might end up with the same situation. So the classifier will find the variable of the mass. It will see that this is a very good variable to separate signal from background, and you will end up in the same situation. So again, high correlation. So you have also to be careful with the choice of variables to prevent all this. So that's all. So for this example, for this challenge. So then, if you end up being tired of working with K-shorted by pi, you could even try to. So the sample is you can find again lambda to proton pion, phi to mu, and other candidates there. So you can start designing the algorithm and the sample to filter lambda to proton pion, for example. This is the example that I've chosen here, and you can do it. So these identifiers, the particle IDs, you can find them in this link here of the PDG. And I think so for this, yeah, this is the sample of how to build the sample for lambda to select lambda to proton pion. So you can, if you want to work with lambda to proton pion, you can start writing your algorithm, your code here at this point. And yes, you can see this is the invariant mass of proton pion, and this is both lambda and anti-lambda hyperons in the proton pion invariant mass. You can see that they peak around the nominal mass of the lambda. So now I think that we can leave 5-10 minutes so people play with the notebook if everyone has downloaded everything, and then we move to the next one. Well, first, if anyone has questions, if anyone has questions. Okay, so if not, I think we can wait till 9:55. I think it's fine.
In the meantime, if people have questions, just shout. I think we will
Yeah.
be connected here.
Yeah, Miguel, I'm having trouble.
Yeah, with. Tibian?
Sorry, can you hear me?
Yeah.
This
Now
is
we can.
Ilhan. Sorry, I was muted and talking to myself. I'm having trouble because where I installed the scripts is not included in the Python path. I needed to add a couple of lines to, otherwise this hep ml thing is not found. I could share with you the couple of lines that I had to add.
But what did you use to install it?
I need to append to my Python path where hep lessons ml is installed.
No, the question is if you used pip, conda, or what did you use to install it?
It should be included. Okay. I'm kind of afraid of using any of those because sometimes they entangle with other things that are already installed. So I did. I already had most of this stuff, so I just.
Yeah, but in general, for me, my recommendation is to use virtual environments in Python. So you have a closed environment where you can install things without touching the system Python installation of your system.
Okay. Then another thing that I found is that in your share notebook, share IPIND, there is a line that is giving an error. In axplot rejection efficiency, the label there, I think there is a misplaced quote. I send you by email, but I had to comment it. And
okay, I'm rerunning everything now.
the one called share IP NB only has one cell.
Which one you said?
I email you because,
yeah.
as I said, I don't have access to the chat. Okay, that.
Did you send it to my CERN email? Because I don't see it. Gibran?
Yes, sorry, I have. I send it to the CERN account, to your CERN email.
Okay, because I haven't received it.
I think, yes. Let me double check. Yes.
Okay. Okay, now I see it.
So there is, I think, it's a misplaced quote mark.
No, I feel it's. I mean, you can see it here right now in my shared screen. It's probably maybe it's because it's Python. You're using Python 2 instead of Python 3.
No, I'm using Python 3.
Okay, so then it's the syntax is correct. I mean, I just executed it. So.
Okay, my bad then. Maybe.
Hi everyone. So, did anyone manage to improve the result or the performance?
Any feedback from anyone? So it's quarter past. Maybe it's better to move to the next part, Miguel. I
Yeah.
don't know if anyone had issues, but
Yes, in any case, because the next examples might be a bit more difficult. So if anyone has troubles either installing the package or with any of the notebooks, even this one or the next one, I think we can discuss it afterwards, right? So yeah, let me go then to the next challenge. Yeah. So the next one is actually working with real data and simulation from the LCV experiment. And the first task is to do the same as we have done before. So select short by pi candidates, but this time working with real data. So I'm loading data and key short by pi samples for simulation, for real data and for simulation, and in them there is a selection, a pre-selection that has been applied in order to remove most of the background. And yes, you can see that even in real data, we get quite pure sample of K-short by pi candidates. Okay, so even with a very loose selection, let's say, you get a huge amount of them and almost no background. But the challenge here is to remove the remaining background. So you can see that this peak is laying over a background that is more or less like an exponential. Okay, so what we want to do is to remove this background here. So yes, again, I mean the procedure more or less the same as before. The difference is that now we have data simulation, so we can use real data as a proxy for our background. So what I have done is to take the candidates from, I think, with a mass greater than this 0.55 GeV to the right. So we use this for as a proxy for background, and then as a proxy for signal we use simulation. Of course, you can play and take as a background proxy also candidates that come from the left side of the dipine invariant mass. Okay, and see what happens. And of course, you have to be careful because you are getting also the tail of the K-short by pi. But still, here you have to choose a region where you are dominated by background candidates and not by K-short by pi candidates. So yes, you see here I'm applying the cut and the selection on the invariant mass, and then again I train the classifier and I do the checks, the different checks. So first for overtraining, the RAG curve, and that's it. Again, the challenge is to select the variables and also to, in this case, also the signal and background proxies. Then also working with real data, there is a more challenging study, which is to select K0 to pi mu candidates. So this is very interesting because it's a decay, the K-short to pi mu, so this can be a K-long or a K-short. And the K-short to pi mu decay was recently discovered by the Claude collaboration. You can find the publication here in arXiv. And at LCV, we can actually see this decay too, and you will have the opportunity here to see it. And the problem is that the amount, so yes, again, we are loading the data. I'm applying also an additional selection requirements, but you can see after you plot the invariant mass, so you can see, so this is K-short to pi simulation in green, in blue is real data, and what you expect as K-short to pi mu in orange. And you can see that we have an overwhelming contribution of K-short to pi, okay, after our selection. This is, of course, this is the pi mu invariant mass. So it's the invariant mass of the K-short reconstructed from a pion and from a mu. Fortunately, we can apply a smart selection in order to remove this peak. And this is done using the missing ET, which is a variable that is similar to, yes, it is also used in other experiments, like, for example, CMS and Atlas. And you can also use the corrected invariant mass. So it's an invariant mass that uses information from the invariant mass itself and the missing ET to get a more peaky structure for K-short to pi mu. Okay, and we can use these variables to apply a selection and remove most of the k-short of pi, and this is done in the next cell. Okay, and when I plot the distribution, you can see that now the amount of k-short pi that I get is negligible, and the data looks really close to our k-short pi menu simulation. Okay. So, but we want to still fight against the remaining background because we have combinatorial background, so background from random combinations of pions and muons, and we want to remove it. Of course, the statistics here is very small, so that's why it's more challenging. So what I have done is to go back and use k-short pi new simulation as a proxy for signal. And then as a proxy for the background, I have used candidates that lie actually on the right, so with a mass greater than 0.55. But of course, here we don't have candidates. So what I have done is to go back to this distribution here and take the candidates that lie on the very right part of this plot. But of course, it's something that you can tune and you can change and see what happens. And again, the set of variables that I use, there is, in addition to k-short by pi, there is another background that might affect the sample, which comes from inelastic interactions with the detector material. And you can use this variable and also include it in the classifier, as I have done, in order to remove them. Yes, then the next is more or less the same thing as we have done before. So again, correlation, the check for the signal for overtraining, in addition to also the ROC curve, and again the correlation of the signal probability with the different masses. Okay, so the idea is that you improve. You can see that here the area under the ROC curve is worse than for the k-short by k. So the idea is that you must try to find a way of improving this, and so it gets closer to 1. So that's really all. So I mean the problems, the challenges are more or less related to the same thing. So they are related. We want to get a pure sample of k-short by pi or k-short pi menu candidates, and fight against the background. And more or less the techniques is the same. The problem is that what you have to use. I mean, what really matters is the classifier that you use, the variables that you use, and also the proxies that you choose in order to deal with this problem. So yes, play around. I mean, I don't know where I should stop, so we switch to the next group. But yes, we can give time. So if people have problems installing or also problems with the notebooks themselves, so let me know if it's fine.
Thanks a lot, Miguel. Yeah, I think we can. So from what I think Gabriel is online, so he can correct me if not, but I think like 1 hour for him should be enough. So I think we can stay online until 11 or so.
Yeah, it's time for me.
Okay, thank you, Gabriel. So yeah, we can stay online until 11 or so, and if people have questions or doubts, just shout.
Okay.
And then yeah, we move to the other part. So we merge this part with the break that we had in mind. So yeah, thanks, Miguel. And yeah, so let's keep around in case people want to ask questions. And I think if you have questions, it's better to ask them aloud so everyone can hear.
Yeah.
I just add the C tau, the head C tau variable, and now the area under curve is 0.93, more or less.
So you're talking about the first one, right?
The second one,
For K-short to pi in real data.
yes.
We are going to discuss some of the models that we trained in the past and now for multiplicity and energy regression. And then we will discuss some of the improvements that we can do to our models. So the R3B experiment is a nuclear physics experiment located in Fern in Germany, which is a facility mainly suited for studies in the nuclear and particle physics field. In our R3B experiment, the branch aims for studies in exotic nuclear structure, and so on. So the experiment is performed under inverse kinematics regime, which means that instead of having a light nucleus or a particle hitting the big nucleus, we accelerate the heavy ion, as you can see here, while the light nucleus is placed in the target position. This allows us to collect almost all reaction products in a narrow cone towards the direction of the beam. So we need smaller detectors in the experiment, which is thankless. In this experiment, we have a full set of detectors, each one in charge of the measurement of one side of the reaction. As you can see here, Neuland measures neutrons, CALIFA is aimed to study light particles and gamma rays, and for example, the glass supermagnet allows us to perform momentum and charge measures on the heavy ion. So this is our detector that is called CALIFA, and it is made of 2,432 cesium iodide crystals, which allows us to reconstruct, yes, to reconstruct us gamma energy and light particles with 5-6% of resolution in energy and 1% for protons at 330 MeV. So the calorimeter is differentiated in two parts. The barrel, as you can see here, which is this part, I think I can draw here, and the IFOS, which is this part covering from 20 degrees to 43 degrees. This part is the most important one, as all the reaction products and fragments are going to concentrate in this part of the detector. So our models are going to have a lot of entries in this part of the detector. So here I present and use R3B root, which is our standard framework for simulation and analysis. Of course, it is based on root, and it is written in C++, which means that it's strongly object-oriented. So our neural networks are going to follow the same structure as all the algorithms that are present now in our R3B root. It uses GN4 as a particle transport engine, and every operation involving any kind of data is performing the so-called task. So every kind of data coming from simulation that is also performed inside R3B root, or data coming from experiment, is managed by this framework. So you can do whatever you want with it. So you can perform analysis on lines, representation, and so on. And here I present you some explanation about the data levels in CALIFA. So real data coming from the experiment is stored as made level, which means that you get the data as it comes from the detectors. For example, in CALIFA, what you get is channel energy, which comes from the preamplifiers that are coupled to our crystals. And on the other hand, you can have also simulated data, which jumps forward into the cal level, which is the calibrated level. From going to the map level to the cal level, you use what is called the R3B CALIFA map to cal class, which converts map level into calibrated level by using these calibration parameters. And this is now a valid input for our models, as you can store here energy that is deposited in the crystals and angles, and so on, the fast and the slow components of the light. But if you want to go one step ahead, you have to go to the heat level, which means that you are performing some kind of algorithm in your CAD level by doing a clustering algorithm. So what we expect is to have a neural network model inside here, so you can translate calibrated level hits from the detector into heat level, which allows you to have information about the primary events that you get in your nuclear reaction. So what we are going to use to perform our training and our models is C++ TensorFlow. So as our R3B root is written entirely in C++, our neural network needs to be developed in the same language. Of course, this is not needed if you have, for example, some kind of root file or data from other experiments, so you can perform a later analysis by using another machine learning algorithms or frameworks like Keras or PyTorch. But if you want to build an inside tool like we are going to do, you need to write this in the same way as it is done. So this is the reason we are going to use C++ TensorFlow. If you want to compare this with another framework for machine learning like Keras or PyTorch, it is slightly faster, from maybe 1.5 to 2 times faster, as we are writing very low level models and we have the intrinsic speeds of C++. The models are highly customizable, as you can do whatever you want with weights, biases, and so on at any point during training or validation and test. That means that, for example, if you want to stop the training at some epoch or something and extract a weight, change it, draw it, whatever you want at any point. So it's very useful to have this kind of features. It is more difficult to develop than TensorFlow Python, and this is not a roast against Python users, of course. What I mean with this line is we have very, very less resources to compare, so it's very difficult to find even a simple model of neural network or something written in this kind of TensorFlow. But when it comes to design a model and train it, I think it's more or less the same as Python TensorFlow. This TensorFlow has its own types as syntax, and this seems that this is very common between machine learning frameworks like PyTorch, as we saw in Andrei classes, so it's not strange. And it has a very tricky installation, so if anyone is interested in install it for any C++ project or something, you can take a look here. And it is more or less well explained, I think. If you have some questions at any point, you can stop me and ask me whatever you want, of course. So now that we have discussed the data levels that we have in Khalifa, let's talk about how we are going to put that information into our models. So we have two ways of doing that, by using raw inputs or manufactured inputs, as we call it. Raw inputs means that you get the hits as they come from the detector, so you don't perform any kind of algorithm on the crystals information or something. So you have two ways of doing that, by using a matrix form, which means that you use a tensor with, say, batch, which usually is 32, 64, 128 for stochastic gradient descent. And MN means the columns and the rows that you are using to translate the phi and theta angles of each crystals into the entry for the neural network algorithm. So it's difficult to implement, as you can see here. This is a distribution of the crystals calorimeter, so it's some kind of unfold Khalifa. And you can see the crystal that most of the calorimeter has regular theta and phi angles. For for each crystals. And of course, the last part of the calorimeter, the IFOS1, is not centered in phi or theta angles. So it's not a regular matrix. And what you have to do is to insert some extra columns or rows so you can put those strange angles or those strange crystals. And it means that you have to use very, very large matrix. So instead of having, I don't know, 60 times 32 crystals, you have 70, 80 columns and another 70 or 80 rows. So it's a bit difficult to translate into a good neural network model. The other way to do this with raw inputs is to put every crystal in a tensor with, say, batch again, 1, 2432, which means that you are putting each crystal in a position in a vector of 1 dimension, and then choose the position of one crystal by its crystal ID, which is the number that is assigned to each crystal. So here spatial correlations are lost or at least not very clear, as you are cutting phi and theta columns and rows and putting all together in the same line. So although your neural network should be able to see those correlations by doing a proper training, this is not a very easy trainable model. So the other way to do this is to perform some kind of changes or manipulation of the data that you get from the calorimeter by using some characteristics for each event. For example, you can get the calorimetric sum, which means that you are summing up all the crystals in your calorimeter, the number of hits that you get, the angular or the energy dispersion or the angular distance, as it is represented in this image. So you get the phi mean and the theta mean, and then you choose it as the origin of your crystals, and then you perform a sum over all the distance from that origin. You can mix this information with some traditional methods like clustering, and you can also get fast and slow components of light, which means that for every particle hitting the detector, you have the light coming from the scintillation process, but as it is not very useful for classifying into gammas, it's useful for making particle identification, as every particle has its own shape of the pulse light. So it could be a useful feature for our models. And of course, you can perform every combination of the previous variables, you can see. So first of all, I will talk you a little bit about multiplicity. So we understand for multiplicity as the number of primary particles that we get from our nuclear reaction. So if you have hits like this in your calorimeter with 4 hits, it's difficult to say if 3 of them were primaries and the other one is a Compton event coming from one of those hits, or you have only 4 primaries, or maybe 1 primary with high energy and 3 Comptons. So as you can see here, it's a very difficult problem to solve. And that's the reason why we are using neural networks. And here you can see represented the problem that we have with this kind of classification. There is no easy boundary or line that you can draw in this kind of plot and say from here to here is multiplicity 1, and from here to here is multiplicity 2, and so on. So it's a very highly nonlinear problem, and it's a very difficult problem to solve, but neural networks provides a very good solution. So this could be a very easy model to classify into multiplicities. As you can see here, the entries of the network could be the calorimetric sum, the number of clusters, the angular distance, or the energy deviation. So in this case, you have 2 hidden layers in your model with 150 parameters, and then you get the multiplicity from the last neuron. So what do you think? Is this the correct way to do a multi-level classification? Any ideas? Of course it's not, because for doing a multi-level classification, as we saw with Andre, what you should use is this kind of model. So you get the same entries and the same hidden layers, but for the last layer, you get 1 neuron per category, let's say. So each one of these neurons is giving you the probability of the event to be classified as M1, M2, M3, M4, or M5. And then you use a proper loss function that for example, the categorical cross entropy. So, which is the same as Andre showed us in the last lessons, but here we are summing all the outputs for each neuron. And with this, you can perform a very good model, as you can see here. And this is the results that we get for some models. In this model, you have 3,700 parameters with 2 hidden layers, very similar to this one model. And in rows, you have the simulated events that we make for testing the model. And in columns, you have the reconstruction of the model. So this number, for example, here, the 82 one, means that for testing events of M1, in 82% of the cases, the model predicts M1 as M1, which is the ideal case. Of course, in a perfect world, this should be all zeros, except this diagonal over here, that should be ones, but of course this is not possible. And you can compare here with a more classic algorithm like the clustering one. Our neural network is close to this performing, but is slightly better and classifying M1 and M5. So it is better for the streams of the events. Well, for M5 is far better than the cluster algorithm. So it's a real improvement over the algorithms that we had in the past. And of course, you can make classification or regression into energies. So your input here should be a crystal array or a matrix array with the crystals that you get in your event. And then your model should be able to predict if your primary gamma or proton or particle has the energy E. So we use a model with 12,000 parameters with 1 hidden layer and 3 discrete energies as a testing sample. Let's say 1 MeV, 2 MeV, and 4 MeV. And what is funny here is that you have represent the best algorithm that you can get that you can use for energy reconstruction, which is the calorimetric sum. So for multiplicity 1, as we are dealing with here, you sum the energy over all crystals, and then you represent it, which is the blue distribution. And then you get the output of your neural network model, which is the orange one, which is almost completely overlapped with. And you can see here, the orange distribution is slightly overfit. It is for the right part of the spectrum, which means that you are overfitting your model. And this can be explained because if you are giving the detector gammas of 4 MeV, for example, 4 MeV, then you don't get 4 MeV in most of the cases. You get maybe 3.9, 3.8, and then your gamma ray makes a compton or something and it escapes from the calorimeter. So you don't get all the energy in your calorimeter. But you are telling your model that the 3.8, 3.9 MeV gamma ray has a target of 4 MeV. So you overfit the model it will shift your energy to the right to compensate this kind of behavior. So you have to be a bit careful with what you do with your training in this case. So it is more critical in this part than its classification, for example. Things that we are going to improve is, for example, put the natural background that we get there in Germany, in Khalifa, into the simulation, so we can perform a very realistic simulation. In this case, for example, we have the spectrum, the natural background that we get in the calorimeter in past March. And this should be implemented in our models, as we can train the models with noise and background, as you were doing in CERN and so on. So this, together with real thresholds and resolutions, plus this black background, makes us be ready for making hyper-realistic simulation events for our neural networks. And other things that we have to work on is the features that you have in Python TensorFlow on PyTorch that we don't have in TensorFlow C++. For example, that loss, the cross-entropy one, is not implemented. The convolutional layers are not very clear how to use them. We don't have the losses that are common to other frameworks, so sometimes it's very difficult to make the training properly, and we are working on that right now. So another thing we have to work at is the particle identification by using those variables that we were saying, the fast and the slow components. And with this, we expect to have ready some models for the experiments that are to come in the next years. So this is all from my part. And if you have the short introduction to Khalifa neural networks, and if you have some comment or questions.
Thanks a lot, Gabriel. So, yeah, I mean, does anyone have any questions for Gabriel? Okay, people seems very shy. I will ask a couple of things myself.
Okay.
One is, because one of the things I know about Khalifa is that the technology, it's somehow correlated to medical physics, and even the reconstruction techniques. So do you think, or is any of these useful in medical physics?
Not yet, because we don't have making any simulation or performing to use in medical physics, but I know there are people working on some detectors that are similar to ours, so you can get coincidences between gammas and so on for uses in medical approach, and neural networks there are giving very good results, but we don't have to perform any kind of studies in medicine or so on.
Okay, it's well, it's a nice application for this kind of studies as well.
Yeah.
That makes it more interesting. And the other question that I have is, but maybe this is because maybe this is a very naive question, but I wonder why, because I mean, you are saying that you are struggling in some cases to use C++ libraries because you don't have, because the rest of your framework is in C++.
Yes.
But wouldn't it be useful at some point to convert somehow your data sets to Python, or your wherever T3 or whatever format you use to store the data into Python, and then to use the Python libraries? I mean, because it seems that would make your life easier somehow, no?
Yes, it will be that. That's what the thing that we were doing the last year with Keras. So we made some models to Khalifa by using Keras, but still you have to install all the R3B classes and so on. And right now for us it's easier. It seems weird, but it's easier for us to have this inside our framework. So we only have to define the class for the training and then use an external macro or a built-in class inside our framework so you can perform your training or something. And of course, if you want to get data and store it in some kind of model or something, then the data that you are getting is coming from the experiment, and maybe it's useful to have that model built inside an online for the experiment or something. So this is a long-term project, so I think it is better for us to start writing this in C++, but yes, it will be easier for us just to use PyTorch or Keras and then perform our models.
Okay, I think it is also nice to see that not everyone uses Python straight ahead for these kind of things, and that there are other possibilities in the market. So, so anyone else has any question for Gabriel? Okay, seems not. So yeah, thank you again. Thanks everyone. So tomorrow we will have our last session of the course. We will have two guests from private companies. So I think this is very interesting just as a counterpart for this more academic part that we had so far. So yeah, please come tomorrow and stay tuned. So see you tomorrow. Thank you. Bye bye.
Thank you.
Goodbye, everyone.